morning. Today I'm very happy to introduce Swastik Kopparty, who is an expert on everything low-degree polynomials, finite fields, pseudo-randomness, complexity, combinatorics, and today he will tell us some related things, even though we don't see, magic and vectors, exactly. So he's an expert he's one of the inventors of the multiplicity codes, and there's this matching vector code here.
Okay, thanks a lot for the invitation. It's very nice to be back in Princeton and nice to see so many familiar faces and new faces. So great. Okay, so I'm talking about private information retrieval from matching vectors and derivatives. This is joint work with Fatima Kashemi, my student at Toronto, and Madhusudan, my advisor. Okay, great. So I will set up the problem of private information retrieval. I will give a tutorial on all the different ways we know how to do private information retrieval. That will cover, let's say, 60% of the talk. And then we'll start seeing a little bit of different things. Okay, so please stop me, ask questions. Good. So here's the setup for private information retrieval. We have a user, and he wants to access a database. And the database is A, which is a vector in 0, 1 to the n. And the user wants to access certain bits of the database. The ith bit of the database, then he wants AI. And the problem is we want to find these bits of the database without revealing to the servers who have the data what the question, which bit of data I'm interested in. Okay, so we have a few servers, server 1, all the way up to server T. And we will send questions to these servers. We will get answers back. So questions and answers. And we want to be able to get AI without revealing I. That's the question. Okay. What does not revealing I mean? Well, what the server sees should not reveal any information about what I is. So this will inevitably be a randomized protocol where the user will sample the question from some distribution, and the distribution from which the question comes will not depend on I. It will be the same distribution no matter what. And such a definition, you cannot make it unless you know that it can be done. So this definition is from CKGS, Chor, Kushelevich, Goldreich, and Sudan in 95. And they already had a solution. They defined it and instantly solved it with a construction. And I think only once you see a construction can you realize what exactly is, what kind of thing we can hope to do. Okay, so I will give you a simple example of a protocol that does this based on low degree polynomials. And then we will see variants and strengthenings and generalizations, and we'll make it all the way to the final construction. Okay, so questions about this model? We have an I, we want to get AI. Okay, so I'm now going to give you an example of a simple protocol that achieves this. We will have T equal to 3 servers. And the quantity that we want to optimize in this construction is the total amount of communication. And this will have order square root n communication. And this is already the protocol of CKGS. And in fact, they get better protocols too. We will see those two as we improve this. But this is the most basic protocol. We'll already see why things can be done. Okay. So our database A, it's an element of 0, 1 to the n. I want you to make it re-index it so that it's 0, 1 to the k choose 2. For k being about square root n. That's the same square root n. Okay, and I will define f. It's a polynomial in x1 up to xk to be the sum over all I and j, aij, xi, xj. This is a polynomial in some field. I will choose the field to be, let's say, f7, just for fun. It's a polynomial over some field like f7, and it's a quadratic polynomial degree. All this is just happening in our head for the moment, or you can think of it as the servers are doing this. They're defining this polynomial for themselves. Okay. And now the way we set things up, any bit that I'm interested in, for example, Aij, is accessible as a value of f. F of and Aij is the same as f of a certain special vector. Zeros with 1 in locations ei, in location I and j. If you put ones in only those two locations, it just so happens, and you can check that this ends up being Aij. Okay, so it is a simple way to set up a polynomial of low degree, which has the desired values at a certain set of points. So this is f7 to the k, and sitting somewhere in there are the points, is your whole database A sitting as certain values. So the problem we need to solve is, so user wants f of some point x for some x. And that is f7 to the m, to the k. Good. And this is the kind of problem we want to solve, without revealing which x it's trying to find out. Okay. And here is the protocol. It is based on this simple property that we've seen in many cases for low degree, for local decoding. A degree D polynomial, when restricted to a line, is a degree D univariate polynomial. Okay, so if you want to get the value at a certain point x, we will pass a line through the point x. It will be a random line, and ask for the values of f at points on that line. If we get enough values, in this case it's a degree 3, it's a degree 2 polynomial. So if we get 3 values, we will be able to recover the value of, we will be able to recover the entire restricted univariate polynomial, and in particular the value at the point we care about. And so this will give us the value at it. So here is the protocol. Pick y in f7 to the k uniformly. The uniformity is what ensures the privacy of the questions. So consider the line L, which is x plus ty. Yeah. And what we're really doing is we're looking at this composed polynomial, g of z equals f of x plus zy. This is the composed polynomial. It is degree 2. Yes. And we can query it at any point we want by asking for f at a certain point we want. So find g of 1, g of 2, g of 3 by querying, by asking the servers 1, 2, 3 for f at x plus, I guess, I, y. Yeah, fine. So that by asking server I for f of x plus I. And this gives you 3 values of the degree 2 polynomial g. We got g. So recover g. Get g of z. G of 0 is the answer. Okay, so this is the most simple private information retrieval protocol. It shows that something non-trivial can be done. What's the non-trivial? With root n communication instead of n communication, there is a trivial protocol with n communication where you just give the whole database no matter what the question is. But with root n communication, we suddenly were able to get something else. We got, why is this private? We should say, so actually, let's see why it's root n. It's root n communication because you are asking the server for f of x plus iy. You have to send x plus iy, the name of the point. That is a point in f7 to the k. K is root n. That's the root n. Why is it private? X plus y is uniformly distributed for an arbitrary x and uniformly distributed y. X plus 2y also, x plus 3y also. So those are the 3 different questions with 3 different servers.
So it's important here the servers can't talk to each other.
It is very important that the servers cannot talk to each other.
It's just impossible.
If
Probably possible.
well, if they completely talk to each other, then it's as though it's one server.
You could do limit, I guess.
And then with one server, you cannot do with less than n communication.
And if they partially talk to each other, is this studied?
People study it, but there's only one limited result, which is that, oh, you don't do a degree 1 polynomial, you do a degree 2 curve. And then the points on the degree 2 curve are 2-wise or 3-wise independent, and you can get a little bit of, but. Okay, so this is it. This is the first PIR scheme that we saw. Okay, so CKGS themselves actually had a better scheme. And it's a bit more, it was a bit more explicit, but later Woodruff and Yekhanin gave another scheme achieving the same parameters with a very nice geometric interpretation. So it will be a small variation of this, which we will see now. So we're going to do T equals 2 order cube root n communication. And this was the parameters were achieved by CKGS, but this is a protocol of Woodruff Yekhanin, and this is from ISO 5. Okay, so what will change is, I can say it in a couple of sentences and then we'll do it. Okay, we'll first change degree 2 polynomials to degree 3 polynomials. Okay, that's easy. I mean, the tricky part is recovering it. The point is, you can recover a degree D polynomial by D evaluations of a degree D univariate polynomial from D values of it. That's true. But you can also recover it from D over 2 multiplicity 2 evaluations, or D over 3 multiplicity 3 evaluations. This is a flexible parameter that maybe we can try to achieve. So what will change is we will still encode our data as a polynomial. This time it will be degree 3. So this will give us this cube root. And instead of asking just for the value of f at a point, we will ask for f and higher order derivatives. From these higher order derivatives, we will get higher order derivatives of g using the chain rule. From enough higher order evaluations of g, we can get recover the full polynomial g and hence g of the original point, which we care about. So that's the whole protocol. I will just write to some things just so that we practice a bit of notation. So that, okay, good. So A is in 0, 1 to the n, which is now re-indexed to be 0, 1 to the k choose 3. And we define the same polynomial f of x1 up to xk to be sum of all I and j, a, I, j, a, xi, xj, xk.
It's not the same K.
Oh, it's not the same K. IJL. And good. And again, A, IJL equals f of some point x, IJL. Okay, so to recover, to get f of x for the general point x, we will pick random y in 7 to the L, not to the k. Define the line. I want to define the line. I want to give it a name. Just I will do this such things again. C of z to be x plus zy, and this is this univariate polynomial in z. Then we consider g of z, the univariate. This is a univariate parameterized curve, which is f of c of z. C of z is a curve, right? X is a vector. Also, yeah, this was a type mismatch. This to the power k. It's a tuple of degree 1 polynomials. So this is a curve, and I plug the curve into the multivariate polynomial to get a univariate polynomial of higher degree. Consider this and get g of 1, g prime 1, dot, dot, dot. No, and then there's g of 2, g of 3. But there are only 2 actually. So g prime 2 by asking for f at c of 1 and all the derivatives df by dxi of c of 1. And the same thing with 2. So this is how much communication? 2K, order K pieces of information. That's coming back from the server. The questions were C of 1 and C of 2. That's the communication going to the two servers. That's also K. This is something that was balanced between these two protocols. Here, the communication to the servers was only K. Oh no, was K, but the return was only 1. Now we got K in both directions. So it feels like we're doing something better. So that's what we do here. And then we got order 2 information at 2 points. That's enough to recover a cubic polynomial. That's why everything's okay. So then get g of z, the whole polynomial from this, and hence g of z. G of 0, which is in this case f of x, as we found. Okay, questions about that? It's again private because the points which you're asking for are 2 points on this random line. Each point itself is uniformly random. C of 1, it's random. C of 2, it's random. Okay, so we had this basic polynomial scheme and we had the derivative improvement to it. Okay, so I'm going to now right. And in that derivative improvement, there was some multivariate. So we had the in both some other themes we'll see again. We have some multivariate object. We have restricted it to a one-dimensional thing and got a univariate object. That univariate object, we're trying to do some recovery for it. In this case, we will recover the whole of g of z and then out of that get g of z, which is what our answer is. We don't really need all of g of z, we just need g of 0. But the way we found it was by finding all of g of z. Okay.
What was the reason you wanted to ask for derivatives instead of just more evaluations?
Oh, each evaluation asked for is a new server. The improvement here was that so this was not so much of a big deal, but we made it 2 servers. The fewer the servers, the better. So the things that we care about is how many servers are there and how much communication is there. And 2 servers already were something non-trivial.
I mean, you could ask for 2 evaluation points from the same server, but somehow you're giving more information to the server if you do that.
That's right. The moment you ask, give me 2 points on that line, I know the whole line, and I know that X is one of the points on this line. So I reveal too much. That's right. So yeah, that's.
And if you ask for derivatives, you're not giving any more information.
You're not giving any more information. It's the same point. You're just asking for more information about that particular point.
Could you also just get evaluations from like a line, like do something second order? Like to get g of 1, you actually can ask like for multiple evaluations over a different line or something like that.
So this is fractal decoding. This to get g of 1, you go to a different direction and you start again. So there may be possible variations. Nothing, as far as I know, improves anything. So getting g of 1 by decoding it from somewhere else. What's the point? Yeah, I don't know. Right. Yeah, I don't know. One small observation is that, we could have gone to even higher order derivatives. But once you go to even higher order derivatives, there are choose 2 pieces of second derivative information. Then that communication is even more, or not k squared pieces of second order derivative information. That's even more than the amount of communication that the user sent. And then it just doesn't balance out. Okay. So now I'm going to give a quick tutorial on matching vector PIRs and matching vector codes. Okay, so that was this. So this was the status of PIRs for a long time. People improved for constant t. The status was the amount of communication was n to the something of t. So 1 over t or 1 over t log t as things improved. and this was the status of how it was, but then things radically changed with Yekhanin in 07 and Efremenko in 09, I guess. And these are these codes called matching vector codes. And yeah, so these are, right. So I didn't say that this is all closely related to locally decoded codes. I'm guessing those are the more famous object and many people already knows. But okay, these are matching vector codes. These are also related to, these immediately give private information retrieval schemes. I'm going to give that. Good. So some definitions. We're looking for, so matching vector family. Matching vector family is a collection of vectors U1, V1 up to UN, Vn living inside. So you have to choose a ring. It's some kind of, yeah, so we're going to take inner product. So it's in some ring to the power k. This is a matching vector family over the ring R, such that UI inner product Vi is 0. And UI inner product Vj is non-zero for all I not equal to j. This is a matching vector family over R to the k. And the question about matching vector families that makes things happen is how many vectors can you get in a matching vector family? And it's easy to see that when R is Fp, a prime field, or even Fq, then N is at most K to the P or something. Yes, this is a maybe P minus 1. So this is poly in K. I'm always thinking of P as a constant. The size of the largest matching vector family you can get over fields is polynomial in the dimension. And the proof is it's some linear algebra because the matrix you make out of the U's and the V's, if you take the inner product, you take the product, you get a 0 diagonal, non-zero off diagonal. Raise everything to the power P minus 1, and it's 0 and 1, 0 on diagonal, 1 off diagonal, and you flip it around and it's identity. And so at that point, it's yeah. So it's ranked. So that says something about the dimension which the UIs live in, and something happens. Okay. So this is the statement that over fields you do not get good matching vector family. But the miracle, I want to say miracle, is that when R is let's say Z6, then you can have N at least super polynomial in K. So in this case, 2 to the log square K.
You want to mention Gomlos, which predated
Komlos?
Gomlos.
Oh, Grolmush. Oh, yes, of course, yes. So this miracle is because of Grolmush, who was studying intersections of set systems, but it's basically the same question. This is Grolmush in 90s. I forget when. You have set systems with restricted intersections mod P, and then if you look at it mod M for non-prime M, then suddenly you get much larger families. And these come originally from the Barrington-Weigel-Rudich polynomials about weak representation of OR mod 6. Okay, so this is some really the constructions are nice and elegant, and I'm not getting into this though. But it has something. So I will say in 3 words how you make it. The fact that it's 3 words is already a hint. Chinese remained a hint. Okay, yeah. But that's not all. I mean, just if I say those words, you won't go make it. But okay. Okay, so I'm now going to take the existence of matching vector families of big size and make a private information retrieval scheme out of them. Later, I'm going to modify the definition to have some extra bells and whistles on top of this. But for now, we can manage with this nice pure definition of matching. Okay. So here is, so this is the Yekhanin and Efremenko construction of a 3-server, no, not 3-server, oh, it's even worse. 6-server PIR with 2 to the root log n communication. So I'm going to define a multivariate object. I'm going to talk about some how that object has the values of our database hidden inside, and then we'll do some univariate restrictions, and we'll do some things. So we have A, which is in 0, 1 to the n, and it's just 0, 1 to the n. Oh, I need some more setup. Yes. I have H6 sitting inside. This is the 6th roots of unity sitting inside F7. 6 roots of 1. And I have a polynomial f of x1 up to xk, which is going to be, so my k was set up so that it's similar, it's like in the matching vector family. I define it to be sum ai x, the vector of variables, to the ui. I going from 1 to n. This is a polynomial whose exponents are the exponents of that, I mean, they come from that vector in the matching vector family. So this is already a bit odd because ui's are elements of Z6. So how do you, how do you do this? Well, this is only legitimate if I promise whenever I substitute, I will only substitute 6th roots of unity. Then it does not matter when you raise the 6th root of unity to the power 5 or 11, it's the same thing. So if I'm promising I'm only going to evaluate at 6th root of unity, then I'm okay. Then this kind of definition at least makes syntactic sense. So this is my definition of f. Okay. Where the UIs come from this matching vector. Okay. So unlike what happened here, we will not be able to recover the value of f at any point. We will only be able to recover the coefficient of x to the ui, ai. This is why this construction gives you a locally decodable code and not locally correctable code. That difference is showing up in what I'm going to do. Okay, so now to recover AI, this is what we do. We'll define a curve. Okay, so we have to pick something at random. So we'll pick first beta in h6 to the k uniformly at random. Oh, I want to draw one more picture. The picture, it's not much, but this is h6 to the k. And on this, I have defined this, I have this function f defined on it. Yeah, so f is defined on this h6 to the k. And that is the place of definition of f. That makes it consistent. So I'm going to pick a beta in h6 to the k uniformly at random. That's why h6 to the k is an important object. And now we'll define a curve. A curve. What is this curve going to be from? I'm going to tell you where it's from. It's from h6 to h6 to the k. It will take elements of h6 and give it. So it's like a parametrized curve inside it. In fact, it is a group homomorphism or affine group homomorphism. So this is CZ, and it's equal to, it's going to be a tuple, right? I will, it is beta pointwise product Z to the, oh, I want AI, I said I want J. Z to the Vj. So first, let's confirm categories of things. Z is a single variable. Vj is a tuple of variables. Single variable, no, tuple of exponents. Single variable to a tuple is a tuple. So it is Z to the Vj1, Z to the Vj2, that product. That's why it is a tuple. Right? So this whole thing is in F7Z to the K. It's a K tuple. And so it's beta 1 times Z to the Vj1, comma, beta 2 to the Z times Z to the Vj2, etc. This is the curve. And when we substitute C into F, something nice happens. Then define G of Z equals F of C of Z to be, no, it's this, and this is sum overall I, AI, C of Z to the UI. I'm going to open it up. Beta pointwise product Z to the Vj whole to the UI. And if you open it up, you'll see the inner product of UI and Vj just shows up there. So this is equal to sum overall I, AI times beta to the UI. Beta is a tuple, UI is a tuple. When you take a tuple to the tuple, you get a one-dimensional thing, a single thing. And Z to the UI inner product Vj. And that's G. And now let's use the fact that this is a matching vector family and something nice will happen. Because this is a matching vector family, UI Vi in this is the only exponent up here, which is 0 mod 6. Everything else is non-zero mod 6. So when you open it up, okay, so I'm following the rules of exponential polynomials where you're promised that you're only going to plug in 6 roots of unity. And in that, G of Z is Aj beta to the Uj. This is some known quantity because I know beta and I know J. Z to the 0 plus some I guess L going from 1 up to 5, the remaining exponents, something, Z to the L. This equality is a bit suspicious. It is, when Z is a 6th root of units. Okay. So let me make this equality less suspicious. I will. Yeah, all this business of taking elements of Z6 and putting them in the exponent, it's, yeah. There's a nice way of viewing it using some kind, it's like some Fourier expansion where you're plugging in 6 roots of unity. That's the nice way of viewing it. Yeah, but there's another way of viewing it, and this will help us a lot later. So I want to do that. So this is this. So actually, what it is this is equal to this mod Z to the 6 minus 1. So a small change of category. This F I'm going to treat as a standard polynomial. It's a true polynomial with no funny exponents. It's a polynomial with natural number exponents. There's no problem in defining it. It's a fair definition. This I treat with natural number exponents. I plug it in and I get G of Z of huge degree. This is degree what is it? 6 square, no, actually 5 times 5, 25. So I'm treating those UIVIs as natural number vectors. This is degree 25K. You see the 25K, it was 5 times 5 for each entry, K of them. So this is a degree 25K polynomial. Let's treat it as that. Let's not play games with, I'm looking at special polynomials whose exponents are in Z6. These are, okay, so now this is this polynomial of degree 25K, and I took it and I reduced it mod Z to the 6 minus 1. And what does reducing mod Z to the 6 minus 1 mean? It means whenever you see Z to the 6, you replace it with 1. So that's the same as Z to the 24 is the same as 1, Z to the 25 is Z. And so it is exactly the same thing as reducing the exponents mod 6. So it's the same thing. So I want to do it this way. Okay, and yeah, so we have G tilde of Z, which is G of Z mod Z to the 6 minus 1. And so it's of degree 5 or lower. And G tilde of 0 is our answer. Well, it's basically our answer. It's A, J, beta to the Uj. Beta is a non-zero vector raised to the power a known exponent. So we can compute this for ourselves, so we can get Aj out. So we want G tilde of 0. And this will give us our answer. Yeah, you can ask me a question. So far I have not given you the protocol, right? This was just picking and defining. We have not done any communication. So now I'll tell you the communication. The communication is, let us find G tilde of 0 by recovering all of G tilde Z. So the user sends C of H for each H in H6 to the server. To server H, yes, that's good. You ask, so there are six roots of unity. So the servers are server 1 omega omega square up to omega to the 5, and you send it there. The server will reply with server H gives back f of C of H. This is G of H, which is G tilde of H, because this is 6th root of unity. Find G tilde of Z. You recover from, this is now just a degree 5 polynomial. I have 6 values of it. I can find the whole polynomial. So I found the whole polynomial. And yeah, we got G tilde of 0. Okay, question.
So it's a new point of view looking at this.
Very mildly point of view, just to let's be okay with this polynomial being a very high degree, and we just go mod Z in 6 minus 1. That's it. Just almost nothing has changed really. We always had this promise that we're only evaluating a 6th root of unity, and which is exactly the same as treating it mod Z to 6 minus 1. Okay. So now we'll try to do it with derivatives. And what this will do is we'll reduce the number of servers, hopefully. We got 6 servers. That's already a bit of a problem, because 6 was the smallest number, which is not a prime power. This actually, so let me just say now, I guess I'm not getting into some details, but so this is a matching vector family in general, something. Yes. You can also talk about not just 0 versus non-zero matching vector family. You can talk about 0 versus in a special set S matching vector family. And Efremenko in his paper, I mean, apparently these constructions not only give general matching vector families, they give you these S matching vector families for special sets S. So for mod 6, it gives you for the set 1, 3, 4. which has some special property. What's the special property? The special property is, in this step, I want to find g tilde of 0. I do not care about g tilde of z, the whole thing. I just care about g tilde of 0. And it turns out that that interpolation problem can be solved with fewer evaluations. Who said that? I mean, what I know about g tilde is that it's a polynomial whose exponents only lie in S. S happens to be smaller. So maybe a fewer number of evaluations, right. No, anyway, S is smaller. So yeah, the number of evaluations you need is just the size of S. So that already reduces 6 to 4. But 4 became 3. And that was because the problem of finding g tilde of 0 from evaluations of g tilde at some number of roots of unity happened to be such that you can do with fewer evaluations. Polynomials with this special monomial structure have abnormally sparse relationships between the values at certain roots of unity and 0. So this can be improved. So can be improved for g tilde with special monomial structure. And it was found by computer search involving some Mersenne prime thing. And g tilde with special monomial structure. Okay. So now I'm going to do the same thing with derivatives. We will make it 2 servers.
And are you going to use this kind of magic?
So no, for 2 servers, we will not use the magic. The magic will help us do things for other number of servers. But for 2, we will see everything, except for the construction of matching vector.
Yeah, basic magic you will be used.
No, just that old magic.
No, this magic, not that magic. This magic is some mysterious magic that, oh, yeah, so they can be improved for g tilde with special monomial structure, that too only over certain fields. So it's over F2 to the, yeah, you can't do this Z6, I mean, the 6th root of unity magic will not happen over F11. It will only happen over fields of characteristic 2 because I don't know why. It's, yeah. Okay, but people did investigate that magic a lot. And the best known PIR schemes came out of finding abnormally sparse or abnormally short relationships between the value at 0 and the value at roots of unity of certain polynomials with certain sparse monomial structure. Okay, so now we see this with derivative. Lots of things are the same, but there's one key change. Okay. So I define, so now the same with derivatives. So now this was done by Dvir and Gopi in 2014, and it will involve some heavy algebra. The heavy algebra was, I'm going to take an object like F, which has coefficients in F7 and exponents in Z6, and I'm going to start taking derivatives of them. When you take derivative of something with Z6 in the exponent, the derivative of x to the I is I x to the I minus 1. So whatever's in the exponent came down. So that Z6 is going to come down. The space in which your polynomial has to be defined, it should have coefficients that can accommodate Z6 in it. So, I mean, the real magic of Dvir-Gopi, it's really miraculous, is that they said, we want a ring which has 6 roots of unity and Z6 in it. So let's make one. Z6 adjoin T mod T to the 6 minus 1. It has Z6, it has 6 roots of unity. Therefore, this is the ring we should work with, and they did. And it was a miracle. I think it was a complete miracle. Everything just worked. So when you move to non-fields, the big problem is, all basic facts about interpolation and all that do not survive. So they did everything until the critical point where you need to find g of 0 from evaluations of g at other points. And there is some linear system that needs to be, there needs to be some determinant that is non-zero for something to happen. And they opened up the determinant, it was some 6 by 6 determinant, and it worked. And And at that point, yeah, they declared victory. So the determinant turned out not to be non-invertible, but it was non-zero, and that was enough for whatever they had to do. Okay, so that's how Dvir-Gopi did it. We will do something much more humble.
But what did they get? A smaller server?
They got two servers. They got the two servers records. So what
With the same 2 to the root log n.
with the same 2 to the root log. So what we will do now is Dvir-Gopi in a simpler way. We will get the same 2 to the root log n, and then using these interpolation, these special interpolation things, it will improve communication for a larger number of servers. But for 2, it does not change it. Okay, so we're not doing it with this. Okay, so we take f of x1 up to xk to be summation ai x to the ui as before. The crucial thing that changes is that we're going to not work over the field f7 anymore. We're going to work over the field f3. Okay, and I'm going to want to do everything that we did before. So that's the same definition. We pick a beta, we define this curve, something, 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 something. We still take a matching vector family over Z6. Right, so UI, VI, it is a matching vector family in Z6 to the K. It's still 6, but this is 3. And we define, okay, so, yeah, so we define, so I pick beta. Okay, so I need to say something more, sorry. So, in F3, there are no 6 roots of unity. There are only, there's only plus and minus 1. So we will just work with that. So we'll think of F as evaluated on plus minus 1 to the K. Define C of Z to be beta pointwise product Z to the Vj. This is still a polynomial with exponents going from 0 up to 5. But okay, it is that. And then we look at f of C of Z. And we define G of Z to be this. And this is, as before, exactly the same sum over all I, AI, beta to the UI, Z to the inner product of UI with Vj. And since this UI with Vj inner products make more sense, I mean, we know only their values mod 6. We will take this and reduce it mod Z to the 6 minus 1. But there's something special about Z to the 6 minus 1 when, there's something special about Z to the 6 minus 1 when we're in F3. What is Z to the 6 minus 1 in F3? So define G tilde of Z be G of Z mod Z to the 6 minus 1. What are the roots of Z to the 6 minus 1 in F3? In F7, I knew they were the 6th roots of unity because this factorizes as Z minus 1 times Z minus 2 omega all the way up to Z minus omega to the 6. 5. What are the roots of this in F3? 1 and minus 1. Anything else? That's it. Then even in F3 closure, how does this factorize in F3? This is Z square minus 1 whole cube, which is Z minus 1 times Z plus 1. So there's 3 roots at 1 and 3 roots at minus 1. What does it mean to take a polynomial and reduce it mod this? It's the same as telling me the value of the polynomial at 1 and its first derivative at 1 and its second derivative at 1. This is the first derivative value, first derivative, second derivative at minus 1. So G tilde of Z, this, is this polynomial is exactly the same information as g of 1, g prime 1, g double prime 1, g of minus 1, g prime minus 1, g double prime minus 1. All this information together is exactly g tilde z. So to get g tilde z, it suffices to get all this. How do I get all this? Well, I ask I get f and its two derivatives at c of 1, f and its two derivatives at c at minus 1, and all that information together tells me g tilde. So I'm done. So I'm continuing the protocol, which is ask server plus minus 1 for f df by dxi df by dxi xi prime at c of 1 for all these k-square pieces of information. K-square piece of information in this case is not harmful. When we did it in the Woodruff-Yekhanin case, k-square was harmful because we were only getting polynomial communication complexity. Now in subpolynomials, so square of subpolynomials already subpolynomial, we're still okay with it. So ask server plus or minus 1 for the values of this at c of plus or minus 1. So there are just two servers, and we ask them for this k-square piece of information. All those are enough to recover it. So from this gives us G. Yeah, I mean, you use the chain rule plug-in. From this, you can get G less than 2 for this is order 2 information at 1 and at both. And this gives you G of Z. I'm sorry, I meant G tilde. Oh, this gives you G, right? And that is right. And G's low order evaluations at plus or minus 1 is exactly the same as G tilde's low order evaluations at plus or minus 1. So I guess this gives you G tilde at less than 2 of Z and at plus minus 1. And this gives you G tilde of Z, the whole polynomial. And from that, you get G tilde of Z, which is what we do. Okay, so this is a small twist, which, what happened? Yeah, so Z to the 6 minus 1 just happened to be, happened to have multiple roots. The multiple roots helped us in that we asked, now there are only 2 points of interest. These 2 points gave us our value. Okay, so ask me questions about this. Yeah.
Is that an equivalence? Like if I give you G tilde of Z for all Z, I'm not going to be able to recover all those 6 derivatives. Or can I? Or can I?
I can.
I can.
Because G tilde of Z is G of Z mod Z to the 6 minus 1. So, yes.
You only have like 3 evaluation points on G tilde, right?
No, I gave you all 6 of these values.
No, that's G. If I give you G tilde of like 0, 1, and minus 1, can I recover the 6 derivatives? No, right?
Yes.
Yes.
Yes. G tilde is a polynomial of degree 5. If you give me these 6 evaluations of G tilde, then I get, then it's order 3 evaluations at 1 and order 3 evaluations at minus 1. That's enough to recover G tilde, the whole polynomial, because it's of degree at most 5.
But if you just get
No, I was asking-
evaluations at 3 points, it's not enough because you need 6 coefficients for G tilde.
I was asking about the other direction because you read equivalent.
I agree. I still stand by what I think I say, which is G tilde of Z. Oh, do we agree that this matrix for G and G tilde is the same? These 6 values, there's 6 values in here. Do we agree that these 6 values are the same for G and for G tilde? It's because of this. And Z to the 6 minus 1 is this. And so.
Okay, yeah.
And this is 6 pieces of information, which is the 6, which is also in the values and just low order derivatives. And so it also recovers. Okay, other question. So what the remaining thing that I want to talk about, which I can, how much time depends on, I guess, how much energy we have. I can is this special magic that sometimes interpolation can be done better.
So can you just repeat how, like what queries we're actually asking and how that relates to, like, you can't just ask for the derivatives of G, is that something?
No, you cannot ask for the derivatives of G. So, good, so we have, this is the multivariate space and F is defined on the whole thing. And there's a curve, I guess this is plus minus 1 to the K. And there's a curve that goes like this. And if what I really care about is the value here and this and the derivative in this, the value of F at this point, the derivative as you move in this direction, and the second derivative as you move in this direction.
That's C.
That's C. The curve is C, the parametrized curve. I want the value of F at this point. I want the value of F, the derivative of F of C of Z. So in that is the directional derivative of F in the direction in which C goes.
Then all the K values and then all the K squared values.
Yes, there are K values and the K square values. So if I reveal to the server that, oh, it's this direction that I'm interested in, it tells me about the curve and that's too much. So I don't want to reveal to the server. I have to really ask the server at this point to give me all directional derivatives. So that's that is harmless information. And from that, I recover the F of, yeah, this is this chain rule thing, right? So I want F of C of Z, the prime of this, that's d by dz of this. This is dou F by dou xi, sum over all I. This is the gradient times the directional derivative times C I prime. C is actually a tuple. So yeah, so this is the calculation that I do inside. I ask for this full gradient vector, and the user personally takes the dot product with the Ci prime vector.
To see if you have a line, because the line, the direction you're looking at, plus the point tells you the entire one. Right? So
Right, but these curves also, they reveal information.
real stuff also.
Okay, so let me tell you, so let me set up what this magical interpolation problem is. So that was a matching vector family. This is now an S matching vector family.
So.
Yeah.
So there's two things actually using it.
Yeah.
One is using S, and the other was getting some new results for more than two servers.
They're related.
They're related.
Yeah.
So you're doing both.
I'm doing both at the same time. Yeah. So we're talking about S matching vector families. And then you ask for the inner product lie in S. I'm going to ask that 0 lies in S just because yeah, it makes some notation easy. So this is S matching vector families. Okay. And this miracle of Grolmur's comes with an extra advantage that it gives you S matching vector families for some small and special sets S. So I'll just say what the statement is. So when M equals P1 times P2 up to PR, for S equal to the set 0, 1 to the R as viewed as a subset of product ZPI, which is the same as ZM. Okay, so a lot happened here. This is the Chinese remainder theorem that says ZM is the same as product ZPI. Within each ZPI, look at the set 0, 1 and look at the R-wise product of all those different 0, 1s. And that's 0, 1 to the R. And we take that set S. It is a set of size 2 to the R. It is the set of those elements whose, when you reduce mod the different primes, you get only zeros and ones. For that set S, there is an S matching vector family of size 2 to the log and log K to the R, sitting inside ZM to the V. This is what Grolmur's and BBR, etc. actually prove. Okay, so for these particular sets S, for these S, there is a special interpolation result, which I will now state. There is a zero interpolating set of size. Okay, so I didn't even say what this means, but okay, let's write it down. It has square root 3 to the n. Okay, this is a result of G et al. I do not. Yes, I'll write G et al. I don't remember the et al. There are 5 authors, and yeah, it was in 2013. Motivated by this, immediately gives improvements to the Efremenko style PIRs. Okay, and what this means is for any polynomial p of x1 up to x, univariate. This is a univariate polynomial factor. For any polynomial g of z of the form sum over all I in S, Ci z to the I. It only takes exponents in S. There is a set V inside the mth roots of unity, which is inside F, we're talking about in F2 closure. So this is in some field of characteristic 2. There is a subset B of size, yeah, with size B equals square root 3 to the R, such that G of 0 can be recovered from values at G of B. G restricted to B determines G of 0.
What is B? B is subset of HN.
It is a set, it's some subset of mth roots of unity.
Okay.
These will be the points at which we would like to evaluate G. We will ask servers for values of F so that I'm now in the non-derivative scheme. We will ask values of the servers for values of F at certain points C little b, little b in B. And from that, we will recover G restricted to B. And these values will then give us G0.
You write that mth root of unity are a subset of F2 closure?
Yes. So this is about polynomials in F2 closure. This is only in characteristic 2. There's something similar in characteristic 3, but they didn't, or there should be something similar in higher characteristic, but this all involved computer searches, so I can't say much. This is true all the way for R up to 104, but we do not know beyond, but it looks like some Mersenne-like thing. So, yeah. So they believe that this things.
So B, the size of B will be the number of servers.
Size of B will be the number of servers. That is the number of values of F that we will ask for.
So it improves only the exponent of the log. I mean, there's no.
It only improves the exponent of the log. That's it.
Yeah.
That's right. And this is the extra interpolation magic that happens. For R equal to 2, this was already Efremenko. Let me just point out, it's trivial that this can, 2 to the R is trivial. That there are sets of size 2 to the R that do this is trivial. Why? The size of S is 2 to the R. And it's a polynomial with only 2 to the R monomials. So there will be some 2 to the R evaluation points that recover the entire polynomial. And hence you can get G0. But it so happens that in some special cases, G0 can be recovered from fewer evaluation points. Okay, so this fact, I mean, this was the best PIR for I guess for some number of servers. I don't know for T at least something 25 maybe. So And it relies on such a thing, and it even in the presence of the Dvir-Gopi method, which did generalize, but it was this somehow beat it. But okay, so in our setting, now that we are using a high derivative version of this, the problem that we need to solve is the following. So we need not just a zero interpolating set. That's what my definition of zero interpolating set was. It is a set of subsets of roots of mth roots of unity such that values there determine the value at 0. Now the exact same problem is it is a subset of the set of mth roots of unity such that the values and higher order derivatives there determine the values at 0. We need a zero interpolating set. Of multiplicity, some higher multiplicity, some multiplicity.
But it will be a fixed cost.
This will be a fixed constant. Yes, this fixed constant.
Related to R and everything.
It will be slightly related. Yeah, it will be unrelated to R, but ultimately we're going to make these, we're going to run these constructions using some analog of this trick, and the multiplicity that we get is going to be the characteristic. And in order for this characteristic to, so it's going to be the characteristic. So yes, we need, but it's unrelated to R. So we need a zero interpolating set of multiplicity E. In other words, it is D inside HM, which is a subset of, I will just stick to F2 there, characteristic 2, such that G less than E restricted to B. This is evaluations of order up to E. I mean, order E evaluations of G at the points in B determine G of 0. Okay, so this is the object that we need, and what the E that we will have available to us is going to be, I mean, it will be the analog of 3 over there, which is the characteristic of the field. Okay, so maybe I will try to wrap up. So let I can. Okay, so yeah, so zero interpolating sets of multiplicity E. So we prove over some kind of black box statement that whenever you have a zero interpolating set of whenever you have a zero interpolating set for some set S, then you get a higher order zero interpolating set down here. There's something I can say nice.
For some set S, you mean inside some set S, or what do you mean?
You use the same set as the one to the.
No, it's a different set S. It's a different set S, but it's the analogous generalization of S to the new P. Okay, let me spend 2 more minutes, and I will state the shape of the general construction.
Wait, you really can be slow, and I feel like I want to slow you down somehow. I feel a bit lost. Can you say, how did we reach F2?
Oh, I see. Good question. We could have done, okay, good question. Let me give you one last PIR scheme, which looks like all these, but it's more general, so it will be hopefully is more clear, because there was 2s and 3s, and it wasn't clear what the relationship between them. Now they will all be well established. Okay, so good. So we'll have an integer M, and we'll have an integer P, which is prime. And we will take HM sitting inside FP closure. I say closure, but it's really just a finite field of characteristic P. And we take, okay, good. And then we let capital M be M times P. Good. And then we'll take SM, which is it's that particular set. SM, oh I see, M and P prime, and HM is an FP closure, and also I guess GCD of M and P is one. I named it. And we have SM, and we also have S little m. What is S little m? It is that set. What is S capital M? It's also that set, except for capital M being it's the analogous construction mod capital M. Okay, so by the way, S capital M is the same as 0, 1 cross S little m sitting inside ZP cross Z little m. S little m is just 0, 1 to the R, mod 0, 1 modulo all the prime factors. This is another 0, 1 mod P, and that's what S capital. So that's what that's what the S capital M and the S little m. Okay, and now so take UI VI and S capital M matching vector family. And SM in Z M to the K. We took a big SM matching vector family, and we define F, which is a map from H little m to the K to H little m. This is this polynomial defined on K variate space, which we will only evaluate on mth roots of unity, and only evaluate and take derivatives at mth roots of unity. And right, and then we define C as before. Right, so then, okay, fine, I'll just define this is beta times Z to the Vj, where beta lies in Hm to the K, fine. And then G of C of Z to the summation AI beta J to the beta to the Vj, Z to the inner product UI Vj, and then this is F of C, and G of Z, which is equal to this, and finally G tilde of Z, which is G of Z mod Z to the M minus Z to the capital M minus 1. Since Z to the capital M minus 1 is Z to the little m, Z to the little m minus 1 whole to the P, and since we're working in characteristic P, this gives us, it's of the form Aj beta to the Vj times 0 plus certain other exponents degree less than n.
Bigger than 0.
And bigger than 0, yes. Z to the positive. And we have access to high order evaluations of G tilde. Why? Because we will ask the server for high order evaluations of F at certain points. This will give us higher order evaluations of G, which are the same as higher order evaluations of G tilde. How many higher order evaluations of G tilde do we need in order to find G tilde of 0? That's what this zero interpolating set problem is. Now what's the 2? P is 2. That's the way this whole business with that F2 can. Everything I said made sense. Now, whenever you have a special, whenever you have this small zero interpolating sets with high multiplicity, that's a situation where we can use it. And we just so happen that we only have them over F2, and so or we only know them over F2. And so that is what we said.
And you know them from this Chiatat or?
We know them from Chi et al. Yeah, it's yeah.
So what's the final result?
So the final result is, I mean, it's a table actually, because the table is the table from Chi et al. But I can state it in terms of whatever we knew for.
You're saving on the number of servers.
We're saving on the number of servers by a factor of square root 3. Is that right? Yes. In the long run, we're saving by a factor square root.
So instead of 3 to the square root 3 to the r, you get 3 square root 3 to the r minus 1.
Yes, that's
The
it.
same communication.
For the same communication, that's it. Or if you fix the number of servers, the amount of communication reduces by some.
Okay.
So in particular, 3 servers, 2 to the cube root log n. That's maybe the 1 point, which is. Okay, and so this is. So is there any questions that? Yeah. So one is this abnormally. So these things, these zero interpolating sets, they were called S decoding polynomials. Having abnormally sparse S decoding polynomials is a mystery, and it is possible, for all we know, is that there are extremely sparse S decoding polynomials, and then that would reduce the number of servers by a lot. So it is possible that there is some improvement we gain from these S decoding polynomials. It seems less natural because I mean it's already using so many specialized facts. Most importantly, the fact that the big S matching vector families we have are for that particular S. So it's really, we're already in a very, very niche area of niche questions. So I'd be surprised if this is the way to get the best PIRs. Yes, but we have no lower bounds at all, which are for PIRs. PIRs have, I'm sorry. So whatever comes from locally decodable codes comes over here. PIRs are even further restricted than locally decodable codes because you have perfect privacy. This is one. And it's also not exactly the same as locally decodable codes because in locally decodable codes over large alphabets, we have this convention that, messages and code words are always of the same alphabet. So if you're ready to relax that, I mean, if you're okay with treating that, the message comes from alphabet 01 and the code words are in the alphabet sigma, then so these are the two gaps between locally decodable codes and PIRs. But proving lower bounds for 2 server PIRs, I think is a really great question.
Thank you. More questions?
Maybe a little bit on that last point. Do you have any personal beliefs about what the right answer should be?
Oh yeah, so I think locally decodable codes and PIR should both be polynomial. So polynomial length for locally decodable codes. For PIRs, it should be polylog n communication. I think that's just because this is such a fluke, right? I mean, there's so many lucky things had to happen. I'm talking already about matching vector codes. So many lucky things had to happen. Yeah.
Which means there must be a better reason why it's true. Or?
Yeah, there should be a better reason why it's true, and once we find that, it will be really good. Yeah, that's just some. Maybe it's a more recent personal belief, having recently understood matching vector codes. Yeah.
That was a beautiful description of all these codes together.
Oh.
Any more questions? Okay, thank you.